And so I just show you this is kind of funny. The idea is to kind of help you remember about the shape of the water molecule, that it's a large oxygen, and the hydrogen is kind of the electron clouds are kind of overlapping each other. That's why this is kind of like, looks like this circle here, this sphere here has been kind of stuck into this larger sphere. Okay, that's what happens. The electron clouds actually overlap each other. That's how this covalent bonding occurs. So if we look at the shape of the electron cloud, it's like a large sphere with a couple of bumps on it over here where the hydrogens are stuck in there. Okay? But the shape of it is the result of this, where the hydrogen, well, if I flip this around, okay? Anybody need me to stay on this for any longer? All right. Then let's move on then to looking at how this applies to how solutions are solvated. How we can use these illustrations to understand how solutions are solvated. Okay, solvation of ionic compounds by water, which is a highly polar solvent. So I'm going to draw a much smaller version of this, okay, just for illustrative purposes, okay? Just a really small version of this.
What does it say after water?
Polar solvent. Okay, remember that the water molecule has a partially negative end. So this is the partially negative end up here where the lone pair electrons are located. The partially positive end is down here where the hydrogens are located. Okay? So if there is an ion, a positive ion on a corner, okay, it's much easier for water molecules to get to a positive ion that's in the corner of this crystal. So around this positive ion, I can get the negative end of water really close to that. So that larger circle is the negative end of the water molecule that's surrounding as much as it can the corner ion here, this positive ion that's on the corner. What's important is I can't draw this in 3 dimensions. It's important that you think, though, in 3 dimensions. And imagine that this is on a corner, a 3-dimensional corner. So more of these water molecules are surrounding this side over here. Okay? So about 3/4 of the surface of this ion can be surrounded by these water molecules when you put this crystal in water. And all particles, if there's any temperature at all, if you're not at absolute zero, and nothing gets to absolute zero, there's movement. This is a crystal. It doesn't look like it's moving, but if you were able to see the ions down at the atomic level, they're wiggling and twisting in place. Okay? And eventually, when the conditions are just right, there's enough water molecules with the negative end nestled up against that positive ion, surrounding that positive ion, and enough vibration of this ion that the need for negative charge is supplied by the water, and it just basically shakes loose. Okay? Provides all of its needs for negative charge by surrounding it, and it shakes loose. And when it does that, then you get a positive ion that isn't just surrounded on three sides, but is completely surrounded by these water molecules. Okay? And again, we're looking at this in 2 dimensions, but remember there's more water molecules around the front and back of this thing. So this forms a kind of water molecule skin or bubble. Around the cation. Okay?
Water molecule what?
Skin.
Or a bubble?
Mm-hmm. Okay, so the same sort of thing can happen. Cation, a positively charged ion. A cation is a positively charged ion. Just set it right here. Okay? So the same thing can happen around these negative ions. But instead of the negative end of the water molecule being attracted to the negative ions, it's the positive end where the hydrogen is located. Okay? So around this negative ion, this anion, then the hydrogen atoms are more attracted. So it's the hydrogen side that is more attracted to that negative ion, the anion. Same sort of thing happens. Enough vibration occurs, and the positive part of the water molecule, the partially positive end of the water molecule, is satisfying the need of the ion for positive charge, and eventually it's going to break loose. Now this is all happening at a very, very high rate of speed. We talk about eventually. Well, these are happening really, really fast. But it's the positive part, the hydrogen part of the water molecule that is attracted to this. Reminding you again, please listen and pay attention. Reminding you again that we're showing it in 2 dimensions, when in fact it's surrounding it on all sides. It's 3-dimensional. Okay? Again, the water molecules form a kind of skin or bubble around the anion. All right, so this whole process is called solvation.
Oh. That's what I meant to
And once the ions are in the solution, they are called solvated. Okay? The process is called solvation. The whole process of partially surrounding the corner here, then breaking it loose and being completely surrounded, that whole process is called solvation. And once that process is complete, the ion is referred to as being solvated.
Hey, Mr. Tucker.
Mm-hmm.
When is his last day?
9 days. 16. I've never seen this mine.
Man, we're going to have 7 more days more than this.
We got like 13 days after
Okay. So this is the process of solvation of ionic compounds by water. Okay. Remember, I said that the solvation process is different for different kinds of solutes and solvents. Okay? Different for different kinds of solutes and solvents. So what we're going to look at now is solvation. Of polar solutes and polar solvents.